In this lecture segment, we'll finish up the text to binary.c example, introduce some more file I/O system calls, talk about a few standard file descriptors that are always open, and do some octal dump debugging. So let's start by resuming our discussion of the program here. Now that the binary file is open, how do we write data into it? Well, as you can see, line 28 loops through the text input file, reading ID, name, and GPA into a struct data. Lines 29 through 31 copy those binary values into the output file using system call write. Now, this call has three parameters. The first is, predictably, the file descriptor to which to write. The second is a memory address from which you want to copy bytes to the file. And you can use any memory address you like. And the third parameter tells how many bytes to copy. A size of operation is typically used for this parameter. And that's it. Write will copy any memory you like from any location into the file. You just tell it the file descriptor, the starting address, and the number of bytes to copy. And there's a partner to write called read, which we'll cover in another lecture, in a later lecture. But we'll find that its parameters are identical to those of write, a file descriptor, an address, and a number of bytes. And the only difference is that read works in the other direction, copying the specified number of bytes from the file into the indicated memory location. Here's question 1. There actually are read calls happening in this program. Where and why? Coming back from a pause, well, as we discussed earlier, the system binary I/O calls are the only way to work with a file, and all the standard I/O library functions, including fscanf, call them. So when fscanf needs to get binary data from the file, it calls read to do so, and then translates the ASCII codes that it gets into internal binary form. Now, line 30 does have one small detail worth noting. It writes the entire name array into the file, rather than stopping at the ASCII null that terminates the string. With a small loop writing one character at a time, we could have avoided writing bytes past that null, but instead we wrote the entire array. And question 2, why didn't we stop at the null with a loop? What would we lose by doing that, instead of writing the entire array? And coming back from a pause, well, recall that predictable size of data makes binary files randomly accessible. Sometimes it's worth a few extra bytes to preserve that, as we're doing here. Now, write is not limited to individual data items. Line 30 obviously writes out an entire array with one call, and we could also have replaced lines 29 through 31 entirely with the commented out call on line 32, which writes the entire struct data to the file in one step. But interestingly, you'll get different binary file contents if you run line 32 than if you run lines 29 through 31. Question 3, why is that? In particular, you'll find that size of data is 32, which is more than the total size of ID, name, and GPA. And we've discussed this briefly in an earlier lecture. Why is the size of data 32? And coming back from a pause, this is a padding problem. 8-byte doubles, at least on the architecture in question here, must start on an 8-byte boundary. But the preceding 20 bytes for ID and name don't end on such a boundary. So 4 padding bytes are added to the struct between name and GPA. And the resultant binary output will have those 4 extra bytes. Now, this is an important subtlety of binary I/O that we didn't discuss in the pluses and minuses section earlier, because it's hard to explain until we get to an example like this. If you write binary data in large struct chunks, the result may be architecture dependent, because padding rules vary by architecture the same way byte ordering does. And for this reason, you'll often see binary I/O done field by field instead of in entire structs. And the final system call in our example is close on line 35. This is past the file descriptor, and it closes the file. It's more than just a nicety, however. Forgetting a close call, especially in a program that opens and closes a lot of files, is a classic nasty bug. To see why, it helps to know that the file descriptor is actually an array index into an array of open files that the operating system kernel keeps for each running program. This array is of limited size, and thus a given running program may keep only so many files open at a time. Closing a file frees its kernel array entry for reuse, in much the same fashion that free releases runtime heap storage for reuse. So forgetting a close has the same effect as a storage leak. Do it too many times and you'll run out of open files. And the classic effect is failure of open partway through the program. And question 4, just to drive this important point home, what error constant does open return in such a case? Do some more external research. Going back from a pause, the constant is en file. So a new topic here. If you actually print the value of out in text to binary.c, you'll find it's 3, not 0. And this would imply that 3 files were already open by the time we did the open call on line 22. And that's the case. Every C program starts with 3 files already opened. These are provided by the operating system with no need for an open call by the program. And they have file descriptors 0, 1, and 2. Let's call these standard in, standard out, and standard error, respectively. As the names imply, standard in is open for reading, and standard out and error are open for writing. Now, in a typical program run, the standard in file is the keyboard, and both the standard out and standard error files are the screen. So, a keyboard is an input file, and a screen is an output file? Yep. Unix has a remarkably flexible definition of file, and other operating systems have followed its lead on this. The essential expectation we have of an input file is that we can read it to obtain bytes of data. And this is certainly true of a disk file, but it's also true of the keyboard. From the point of view of your program, the keyboard is an input file from which may be read the ASCII characters you're typing. It's a kind of slow file, and every once in a while it requires an hour to read the next few bytes because you left for lunch in the middle of a program run, but it's a file just the same. You've already seen this from the user standpoint. You know, for instance, that the keyboard input has an end of file marked by Control-D in Unix. The program view of this is the open standard in file descriptor 0. And similarly, all we expect of an output file is that we be able to write bytes to it. And the screen certainly qualifies. When your program writes ASCII codes to file descriptor 1 or 2, standard out or standard error, they appear on screen in normal situations. You're also familiar with file redirection in Unix or Windows, using less than or greater than to cause a program to read from a file instead of the keyboard, or to write to a file instead of the screen. All that's happening when you redirect input or output is that the shell program that runs your commands arranges with the operating system to set up standard in and standard out file descriptors that read from or write to files instead of the keyboard and screen. Your program is none the wiser and simply thinks that you've become a really fast typist. This is a good example of the elegant design that comes from a broad interpretation of file. This flexible definition of file extends further than just the keyboard and screen. If you open an internet connection to a web server, say, each end of the connection appears to be a file with an integer file descriptor. One program sends data by writing to this file, and the other receives it by reading from the file. In an upcoming lecture, we'll set up something called a pipe between two programs that works similarly. So why are there two output files, standard out and standard error? Because when you redirect output to a file, there may be some data you still want to appear on screen. If your program prints an error message warning this will erase the disk, you'd like the user to see that on the screen rather than have it redirected to a file. When you redirect output with greater than, it's only the standard out that goes to the file. The standard error remains directed to the screen. These three standard files appear at the binary file level as open file descriptors, but the standard I/O library also represents them as the file pointers standard in, standard out, and standard error. We'll look at just how those work in the lecture on the standard I/O library, but for now note that fprintf on standard error writes to standard error, file descriptor 2, while printf writes to standard out, file descriptor 1. By convention, error messages are fprintf'd to standard error, as on lines 24 here and 26. Now, finally, let's look at the file our program has created. The listing in the diagram is an octal dump of students.out, which is produced by the Unix OD utility. Similar binary file dump or editing utilities are available in any operating system. They show the file content byte by byte, usually in hex, or in the case of 70s vintage applications like OD, in octal. This particular listing, with the OD-BC command options, shows 16 bytes per line in octal, and then repeats them on the next line as a character if the byte holds an ASCII code, or as an octal value if it does not. The second line makes it easier to see which byte values are characters from the name strings. And finally, along the left, are the file offsets at which each line pair starts, also in octal. So, for instance, 0020 represents offset 16. Now, deciphering an octal dump is a critical debugging skill if you're working with binary files. So let's piece through the OD dump and answer these questions. Question 5. Where does this first byte of 012 come from? Is that really an end-of-line character like it shows in the second line here? Note that this was produced on a little endian machine. It matters. Coming back from a pause, it's an end-of-line if you look at it as ASCII, but it's really the least significant byte of Staley's ID number, which is 10, if you look at the text input here, and that is, of course, octal 012. It's interesting to note that there's no way to tell what type the binary content of a file is, e.g. an ASCII code or the first binary byte of an int, without knowing how the program that wrote it generated the output. Question 6. Where does the data for Staley's name begin and end in the binary file here? Well, answer 6. We wrote out the entire array. So it starts 4 bytes into the first line here and ends 16 bytes later, 4 bytes into the second line. But you could also say that it ends with the 0 here, which is the ASCII null that terminates the actual string content. Question 7. What is the 014 byte here near the end of the second line pair? Where does that come from? And what are the 8 bytes that precede it? Returning from the pause, that's the ID for Wu, decimal 12, octal 14. And it's preceded by the 8 bytes of Staley's GPA. Now, don't try to read those 8 bytes. Floating point binary representations are crazy and not really generally decipherable. Question 8. Why is there an LY after Wu? And coming back from a pause, that's just leftover garbage from the Staley that was in the name prior to Wu. The null after the U means it'll be ignored.